Good to see you. So we'll continue with what we were doing, and we were looking at transformers, which would relate to your assignment, question 1. Come in. Yeah. Okay. Now we'll continue with this. I answered whatever questions we had on the study desk. If you have any questions, do send them to the put them or post them on the study desk, and I'll answer them as quickly as I can. Last week has been a bit busy for me, so I was a bit delayed with my answers, but I have done that. I have also set up some discussion area there for question 1, question 2, etc. of the assignment. Okay, so we'll continue. I must say that I have put a note there that about an error in our intro book, where I say the intro book hasn't been updated. Our exam used to be open book, so the intro book is still saying that. Which is, of course, not right. The exam is closed book, as you would see when I give you the sample exam paper. And if you look at last year's exam, you would see that this is the case. And also, I have put a note on my welcome page, and I've said the exam is closed book. Okay, so I'll continue with the transformer, and I had drawn a little diagram of a transformer on this side, and I'll do that again because every now and then we would refer to it. I won't show that side. I'll just save time and draw it on this side. I had a winding close to the core, and I said that normally that would be the low voltage winding, LV, and normally the other one, which we have around here. I suppose I can draw it in black. This other one could be segmented, like you see there, and that's the HV. So I'll leave that like that. Later we'll come back and refer to it. The transformer that we were looking at, we said we could think of it as an ideal transformer. And with ideal transformers, you say that you know everything there is to know about them, and everything there is to know means this voltage ratio would be equal to the turns ratio. There would be some current, normally shown like this. Like this. And that's a perfect transformer. And for the perfect transformer, E1 on E2 equals N1 on N2, and I1 N1 equals I2 N2. So we discussed that in detail last week. And that, as I said, that's all there is to know about a perfect transformer. If you know that, you know everything. And you can then use that to do your work. I must say something philosophical here. Yes, when you learn that, you know this. Just remember that this is just a tool that you understand. There is always a next step, and the next step is to use it in practice. And what I find is, I communicate with my previous students all the time, and they ring me up, we talk about things. And what I find is the challenge is the application of the tool. So anybody can say E1 on N1 equals N1 on N2. And, E1 on E2 is N1 on N2, and I1 N1 equals to I2 N2. But recognizing when you should be using that and when you shouldn't be using that, is a challenge. So, and that's work. That is more work out there. People pay you to do this rather than education. So education means you understand it. You understand the tool and you practice using the tool a couple of times. And then you go out and you use those tools. And people pay you money to do that. So that's a separation there between, well, it's not completely separate, but it is, education is one thing, and using what you have learned during your education to do something in practice, that's the next challenge. So don't say that, oh, I know everything now. You never know everything. You never know when it's going to be useful. So the trick is to just put this in the background and say, one day I might need it. And I have to learn to use it, and I have to learn to use it properly in a disciplined way. So that's why they call our area, the electrical engineering discipline. It's a discipline. That is, you use those things in a very defined way, in a disciplined way. Anyway, let's continue. So we talked about this. I can't quite remember where we were, but we certainly would have talked about resistances. So we said, this is perfect. This is a perfect transformer. And then we said, real transformers would have imperfections. And we would have said, oh, this is one imperfection, R1, and R2 there is another imperfection. And we said we put them in series because this is an I squared R loss. The loss, the amount of loss is proportional to the current going through the windings rather than the voltage that we put across the windings. And I think we did talk about core losses. We said in addition to the copper loss, we got core losses. Now remember, we call them copper loss. Maybe winding loss is a better name because there are situations where we are not using copper. I do hear that in some situation we use aluminium. So remember, the idea of copper loss is probably better to say that this is winding loss. The other losses, and losses can only be represented by resistances. You can't use inductance or capacitance to represent loss, because when we talk about losses here, this is dissipative loss. This means something converted to heat. And with a capacitance or an inductance, they don't convert anything to heat. Only resistance can. So that's why we have resistance representing our core loss. And as I said before, if you want to know the details of core loss, look at your power electronics notes. I do have more details there. But in general, the two losses there are eddy current loss that we reduce by laminating the core, and you have hysteresis loss. And with hysteresis, you reduce hysteresis loss by using the right steel. See, for transformer steel, you would have particular grade of silicon steel that you would use. And these have been specifically designed so that they've got a thin, what we call a thin hysteresis loop. If you have a hysteresis loop that's fairly big and fat, then that's a lot of loss. And again, if you want details, look at my power electronics notes, which I think Les Beutel is still using. So look at that, and you will see the details there. For now, we'll just say that there is some core loss, which is made up of hysteresis and iron, hysteresis and eddy current. So we say core loss or iron loss. So that's represented by this, core loss or iron loss. There is another name people use, which is called no-load loss, or no-load loss. No-load loss. So all these mean the same thing. And this resistance is normally represented by R0. It's normally called R0. So that's another imperfection. Any questions about the core loss? It is an important loss in a transformer if you're dealing with the running cost of transformers, then that comes into it, because that's sitting there all the time. This one here is variable loss, so it depends on how much demand you have, whereas this one is fixed loss, which means that you're losing that all the time. So if you look at the running cost of the transformer, that can be a big factor, especially if that transformer is lightly loaded most of the time. Then this could be the one that determines the running cost rather than that one. If you have a transformer that's on full load all the time, then that is a big factor as well. Okay. Why is it in parallel? And we said it's in parallel because the loss here is not an I squared R loss, where I is a winding current. The loss here is more the applied voltage squared. It's more proportional to applied voltage squared. So that's why we put it in parallel. And it so happens that it is the case because it's proportional to the amount of flux in the transformer. So that's why it's a... Okay, so two imperfections then, core loss and winding loss. Any other imperfections for your transformer? Leakage flux, that's good. So leakage flux is that. And with leakage flux, there are two ways of looking at this. One is simple but not realistic, and another one is a bit more realistic. So I'll start with a simple but not realistic. So let's start with a simple way of looking at leakage flux. So let's say that you copied your textbook literally, and you made a transformer that looked like this. So primary side there and secondary side there. So that's your transformer. As I say, we don't build transformer that way. Not normally, anyway. But let's say you did. And if you did, you would quite easily see that this... I hope the video sees blue. Does it? You don't know? You think? Yeah? Or should I do it in red? I'll do it. Oh, it's a bit pale, this one. Let's try that one. Still a bit pale. I'll do it in blue then. Okay. So this is a flux line. Sorry about this. I'm trying to make it as dark as I can. So that's a blue flux line there. So that's a flux line. I'll draw another one like this. So that's a flux line there. Of course, those flux line, half the time they go in this direction, and half the time they go in the other direction. They go up and down, etc. So let's look at those. And this bunch of flux lines, we could give them a name. What sort of name would you give to this bunch of flux? Any idea? Give it a name. It could be given quite a few names. I'll give it a name starting with M. So what do you think the name would be? That's very general, but I want to be a bit more specific. Mutual. Yes, very good. Thank you very much. That's mutual flux. Mutual. What does mutual mean? Mutual means it's linking both circuits. It's mutual. Mutual means... Is there another word for mutual in English? Mutual means both. Right? Both. It's linking both. So that's mutual. Some people call it mutual flux, which is quite fine, quite okay. Another one could be core flux or core flux. And some people call it main flux or main flux. Which one is my preference? My preference is mutual flux, because that really describes it. Again, I'm so worried that this isn't shown on the video. So it's mutual flux or core flux or main flux. Mutual flux is my preference because it emphasizes that the flux links both the primary side and the secondary side. Okay, so how about this one here? There would be some amount of flux that would do this. Roughly, what percentage of flux do you think would be mutual flux in the core compared to flux that will jump out in air? Of course, this is air here. What percentage, roughly? 99? 99? I'll go for about 97. Depends, yeah, it depends on a few things, but practical transformers would have leakage flux of the order of a few percent rather than 1%. And why is that? Why is it that more than 95% typically of your flux would be in the core and only about 5% or so would leak out? Why is that? What's the fundamental reason? Permeability, that's right. That's the key word, permeability. Permeability. Permeability is the ability of a particular material. It's a material property. So permeability is a material property. And it tells you something about the material. It says that with this material, flux would very much prefer to flow through it compared to flowing through air, say, or vacuum, because flux can go through vacuum as well. So this is made of iron, therefore it has high permeability. And this is air here and air there. They have low permeability. Now, this is power systems analysis. You're hoping to be power engineer. And you might go to an interview one day, and if you have people a bit like me on that interview panel, I'll probably say to you, okay, I may not do that, but say I might say, okay, how much more permeable iron is compared to air, typically? Typically, how much more permeable would iron be compared to air? In other words, what is its relative permeability? What is the relative permeability of iron typically? And that's the reason we will be using it to make a transformer rather than use timber. Timber is cheaper, but we don't use timber to make a transformer. We use silicon steel because silicon steel has got more permeability. And you can either talk about absolute permeability or you can talk about relative permeability. That's fine. All you have to do is multiply the relative one by mu naught, and mu naught is 4 pi times 10 to the power minus 7. I remember because I taught fields and waves last year. You don't have to remember. You just Google it and you will see what it is. But the relative number, though, how much more is iron more permeable than air? It's good to have an idea of that. So what would it be, you think? About 1,000, yeah, about 1,000 times. About 1,000 times if the iron has got a bit of flux in there, reasonable amount of flux. Of course, if it has got very, very little flux, then it would be more than 1,000. It would be about 5,000. As you put flux in, the iron becomes a bit less permeable. And then indeed there is a point where the permeability will suddenly drop and become as bad as air. And what's that point? What do we call that point? Saturation. That's right. Saturation. Now, yeah. So if you're power engineers, I would expect you to know what saturation is. So this ion has got very high permeability at first until the flux density in there reaches approximately how many Tesla? How many Tesla before you hit saturation? For iron, for silicon steel, how many Teslas before you hit saturation? That is what sort of flux density? Well, is it 5 Tesla? Or is it 0.1 Tesla? Right. Silicon steel, these days, 1.8, 1.7? 1.7 Tesla, and beyond that, you will hit saturation. Approximately that, it will depend on the grade of steel, but the rough number would be somewhere around that value. Okay, so bunch of flux here. We have mutual flux, or core flux, or main flux, and then we have this one. I asked you to name that one, and we've named that one, core flux, mutual flux, main flux. What would you call this one? A name for this one? Of course, there's a bit there as well. But what would you call them? Yeah, you will call it leakage flux. I would like a better name. What would be a better name, or qualify it more? What would you call it? Leakage flux, yes, but qualify it more. I'll give you a hint. When current flows in this one, there would be leakage flux here as well. So what's the difference between this leakage flux and that leakage flux? Maybe I'm not giving you enough hints. You have to give this different name compared to that. They are both leakage fluxes. That's right. Yes, that's a primary side leakage flux. Primary side leakage flux. And this is a secondary side, secondary side. It's a terrible piece of board here. I'm sure I can rub that off now and write secondary side leakage flux here. Secondary side leakage flux. Sorry about the noise with this thing. Okay, so primary side leakage flux, secondary side leakage flux. That's good. Okay. How do we represent flux in a circuit? I don't know. I'm confusing a little bit now because I'm running another class for protection. But I think we came to a point. Did we come to a point with this class where we talked about flux and the definition of flux and the definition of inductance? I think we did. Very good. So we can represent those 3 bunches of flux by 3 inductances. Right? Now, in reality, like if I look at the flux here and you forget about secondary, let's say you energize the primary, you don't have secondary, you have exactly the same current causing the flux to flow, but we, in our diagram, in our model, the model is not the transformer, it's just a representation of the transformer. In the model, we separate those fluxes and associate them with separate inductances. So let's start with the easier one first. The easier one would be the leakage flux on the primary side. We'll represent that by an inductance. And I did say last time that there's no magic about an inductance. It's defined. An inductance is the constant of proportionality between the amount of flux and current. So anything that creates flux, when you push a current through it, has inductance, and the amount of flux per ampere is what inductance is. I will put a video that's dedicated to that, so you can watch that. But every time I say inductance, what should come to your mind is a bunch of flux created by a current. And the amount of flux per unit current is the inductance. As simple as that. You don't have to read 10 books on it. No point reading 10 books on it. That's what it is. So when people say inductance, you know exactly what it is. Okay. So there is an inductance then associated with the leakage flux, and we put that inductance here, and we call it primary side leakage inductance. Normally called L1, so we'll just say L1 there. Now, the legitimate question to ask is, why is it put in series with the winding current? And the answer to that is that the amount of leakage flux is proportional to the current in the primary winding only. Because that's what you would expect. That's why it's leakage, because it has no association with what's happening on the secondary side. It depends solely on the primary current, and it depends on the winding, the winding current. So we put it in series. Okay, so similarly then, on this side, if there was current flowing on this side, you would have this here. So that's your third imperfection. So first imperfection, winding loss. Second imperfection, core loss. Third imperfection is the leakage. Now, when we talk about leakage, I said to you, it's easier to show this with this kind of transformer, which we normally don't build. This one here shows clearly primary side leakage and secondary side leakage. Now, when you get to a practical transformer, which is more like this one, and that's only one leg of that transformer, normally you would have 3 legs for 3-phase, but I've shown just one leg, but that's enough for us to explain what's going on. So in a practical transformer, which is different from this one, you still have your core loss, which is there. Sorry, core flux. Your core flux, which is there, or your mutual flux. Now, the question is, where is your leakage? Where is your leakage flux? I'll just say what the answer is. You think about it, and you, when you go home, you think about it. Leakage flux, it so happens, which is definitely true, is there. So that's the LV side leakage flux is there. Bit hard to draw, but I will do my best. So that's the LV side leakage flux. So what I've just drawn there, that path, is the LV side leakage flux path. I normally associate my lines with a path. That's a leakage path. This is a mutual flux path. I could put the word path there. So that's a mutual flux path. That's a LV side leakage flux path. If you really understand this, I don't know whether you do, but if you really do, if you really make an effort, you would see that this mutual flux path, can you see that it links, that is, it goes through both the LV and the HV. This is HV. LV is this one here. LV is this one. So you can see the path that goes through the core, the mutual flux path, it goes through both LV and HV. Now, if there is a path, flux will go through it. That's one of those things about flux. If there is a path for it, it will go through it. It will take it. Of course, there will be some paths that are preferred, like the one through iron is preferred. But this LV winding, it also sees a flux path there, and it will take it. Maybe only a few % of the flux will go there, but still it will go there. Now that's the flux path. Now can you see that the black flux path, which I've just drawn there, does not link the HV winding. It doesn't link it. It goes in and out, but it doesn't link it. Whereas that one goes like that, and it goes through it, so it's linking it. This one doesn't link the winding on the outside. Can you see this? Unless you fully understand what flux and flux linkage mean, you may not see this. So I ask you the question. The black flux path, does it link the HV winding? You can see that it doesn't. So that is the flux path for LV side leakage flux path. How about HV side leakage flux path? So HV side leakage flux path. Can anybody see it? Where would the HV side leakage flux path be? So I've given you a very good hint. I've told you where the LV side leakage. Of course, there's another one. Where we have asked too many questions now. Let's go one by one. So first one, where is the HV side leakage flux path? That's right. It will just go around that. So it will be still through there, but it will link only the HV side. So that's the HV side leakage flux path. Of course, I haven't shown you on this side. It will be the same. So you have a leakage flux path there in that gap, and another one there going through the gap there. Okay, we get a little bit practical now. Whenever when you're working, you may have to procure. You understand the word procure? It means you buy one. You may have to procure a transformer. In which case you have to specify that transformer. And very often, and I hope you do, if you ever do that, you would specify this transformer. You would say, I would like the leakage to be so much. Sometimes you want it to be as low as possible. Sometimes you would like to specify it. And I will talk about why you would like to specify it later. Typically, for 11 kV distribution transformer, the leakage is in per unit. We'll study per unit later. But in per unit terms, it's usually about 4%, 5%, maybe 6%, around that percentage. But sometimes you might want it to be a little bit higher, and I'll tell you why later. So if you wanted to have a bit more leakage flux, you could tell that to the supplier, to the manufacturer of that transformer. You could say, look, please, Mr. or Mrs. Supplier, could I have a bit more leakage, please? And they would say, okay, it will cost you a little bit more money. Right? So what do you think they will do to give you a bit more leakage? And there are situations, as I say, where you might like that. So a bit more leakage. How would you get that? That's right. So you increase this gap here. You would make the HV more separate from the LV, have more gap here, and that would give you more leakage if you wanted it. On the other hand, you do have situations where this gap would be big anyway, giving you probably more leakage than what you want. And why would that gap be quite big? This gap here in between the LV and the HV, why would that gap would have to be made big? Insulation, that's right. So you may have a transformer where you need so much insulation anyway that the gap between LV and HV is so big that you're getting more leakage than what you would like. Too much leakage, no good, and we'll discuss why later. Too little leakage also can be no good, and we'll discuss that later. Okay, so leakage then. We've studied leakage, I think, enough now. What other imperfection do you see for this transformer? There are a couple others. There's one that's important. There are others that are also important, but that for the purpose of the course we will ignore. But there's one that we should not ignore, for now anyway. And what's the one? So what's the fourth imperfection? Yeah. I will not call it energy, though. I would not call it energy. The reason for that is, if you're magnetizing a core, when you magnetize a core, you would need magnetizing current, that's for sure. Right? However, there's no net energy associated with that. This is not like a resistance. With a resistance, there's a net energy because you're losing energy. But with this one, you're not losing anything as far as power is concerned. You, of course, have to input energy into it. But when you input energy and then extract it later, on average, you're not taking anything. And you will see that that's the case here. Whilst you will not need energy, you will need current, though. You will need some current to energize the core. And what do we normally call this current? You call it the magnetizing current. So you need a magnetizing current. And this is an imperfection. I talked to a very experienced engineer, must have been about 3 years ago, and he says, Tony, that's not an imperfection. No. And I say, well, if you go back to your perfect transformer, check whether it has got any magnetizing current. It hasn't got any, because you assume whatever current goes in comes out. That's what a perfect transformer is. And indeed, if you were to, if you were granted a wish, and you said, oh, make a wish about your magnetizing current, what value would you give it? If you had one wish, what value would you give to? You could make it any value you like. What value would you give to your magnetizing current? Zero. You would say zero. And the fact that you're telling me it's zero, it means that the ideal perfect transformer should have no magnetizing current. How do you translate that to material property? What material property would allow you get a transformer that has got zero magnetizing current? I could ask you the same question about, say, a resistance. I would say, if I wanted a conductor that has got zero resistance, and that you'd make a lot of money if you had that conductor with zero resistance, what material property would be associated with that? In other words, what's the property of the material that would be needed to create zero resistance wire? High conductance. I am hoping that we, of course you're right, but I'm hoping our language improves as we go through this course. So thank you very much. So high conductivity. So you will have, if you have a material with infinite conductivity, then that material would have no voltage across it. So for no voltage, you could get current to go through it. So that's the electrical side. Now we talk about the magnetic side. So with magnetics, you would like a material such that the magnetizing current is 0. In other words, you would like flux to go through that material without having to put too much current, indeed 0 current, in the coil that you wrap around this material. So what material property would you like that would give you flux for 0 magnetizing current? So I want flux for no magnetizing current. I want flux with no current. What material property should I be looking for?
Find inductance material?
No, again, our language, inductance is not a material property. Reactance is not a material property. Material properties are like density, conductivity, resistivity. These are material properties. That's right. So what permeability would you asking for if you wanted 0 magnetizing current? Infinite. That's right. So unless you can translate those things and link those things together, one of my colleagues wrote, I asked for some feedback from my colleagues. So I am, so happens I'm the head of school, so I asked feedback from the lecturers, and it was written very big, compartmentalization of knowledge. That is a problem. And that is a problem. And I can see the problem now because, yes, we've heard permeability before. We know what magnetizing current is. We even understand that we should get it as far down as possible, but we are not linking it with permeability. So that's compartmentalization. You have to take the little bits of knowledge that you have and link them. So you will be linking magnetizing current with permeability if you realize that you as an engineer probably would be trying to get your magnetizing current to come as far down as possible. And in order for you to do so, you got to get material with a certain property. And that property is the permeability property. And you would like that permeability to go high and high and high and high. And if you want your magnetizing current to be 0, then the permeability has to be infinite. What is the conductivity of the winding in a transformer that is perfect? What is the conductivity of the winding in a transformer that is perfect? Infinite. What is the permeability of the core of a transformer that is perfect? Infinite. So in your perfect transformer, when before I said, oh, you know everything there is to know about a perfect transformer, so I am starting to think whether you really know everything. Well, hopefully you know now. So a perfect transformer is V1 on N1 equals N1 on N2, I1 N1 equals I2 N2. But we also have to realize, when we've made those two statements, that we have implicitly said that this perfect transformer is made up of windings that have this material property, that is, the conductivity of the windings is infinite. And it's got this other material property, that is, the permeability of the core is infinite. So therefore, this here, this transformer that we say is perfect, it has 0 magnetizing current, because in it we have a core that is of infinite permeability. So what we do, we artificially say that we are telling a lie. This transformer is not really perfect. We say there's an additional current that will flow, and this additional current is the magnetizing current, which we normally call Im. Now, the magnetizing current, all our currents, before I say this, all our currents we could describe them. We could say oh, this is a resistive current, or this is an inductive current, or this is a capacitive current, right? Of course, there will be mixtures, because some currents would be a mix of inductive and capacitive, depending on what voltage you are relating them to. A magnetizing current, is it a resistive current? No. Is it a capacitive current? No. And it can only be 3. So it must be an inductive current. And that makes sense, because associated with it is a certain amount of flux. So the magnetizing current is a current that you need to set up a certain amount of flux. So because it is inductive, we show it. We show it as an inductance, and that inductance is called Lm. Lm. Again, I'll use the board here. So that's a magnetizing inductance, Lm. And of course, you want Lm to be as high as possible, tending towards infinity. So that's a fourth imperfection. In reality, we should not have, sorry, not in reality, but ideally we should not have this branch. But in reality, we have to have it, because there's no such thing as infinite permeability. So you can see here our philosophy. Our philosophy is to say that reality, so this is reality, in this box is reality. And by reality I mean practical. So practical or real. So that's practical or real transformer is equivalent to ideal. So this is ideal there. Again, I'm drawing everywhere, I'm putting lines everywhere, but hopefully you see what I mean. So this is ideal here, perfect. That's perfect. So practical or real transformer is equal to perfect transformer. Perfect transformer plus imperfections. Okay, just imperfections. So that's the philosophy we are using. So the transformer, which is the outer thing, is a transformer. These are the terminals of the transformer. We can't get in there. In practice, we can't get in there, but we can picture what's in there. So in there, we can imagine in there. We imagine something perfect, plus the 4 imperfections that we have covered today. This one is in parallel. The magnetizing current is in parallel because it is proportional to the voltage that you apply. It's not proportional to the current going through the winding. Okay, so we have left out one more imperfection. We have 2 minutes to talk about it. We normally ignore it at 50 hertz, but at higher frequencies, you will have to take it into consideration. So what's this other imperfection that we have not worried about?
Must be something with capacitors.
Oh, very good. Excellent. Yeah. So the transformer is big pieces of metal separated by insulation. And when you have big pieces of metal separated by insulation, you have capacitance. So the transformer would have interwinding capacitance, normally represented by capacitance from there to there. Interwinding capacitance. What other capacitance you would have? So interwinding, because you've got HV copper, LV copper, in between them insulation, So you have interwinding capacitance. Any other capacitance? That's right. Winding to earth capacitance, or winding to core, if you like. And there is another one that's mentioned from time to time, and that is turn-to-turn capacitance. That is because from one turn to another turn, you got inductance. But you also have, from one turn to another turn, you have insulation. So that creates capacitance. So turn-to-turn capacitance, winding to winding capacitance, and winding to earth capacitance. So you take all of these into consideration, and you have to, if you're looking at this transformer under high-frequency conditions, and one of those high-frequency conditions could be a lightning strike. So if you have a lightning strike, the distribution of capacitance would decide where the maximum stress is on that transformer, because the stress is not uniform at high frequency. At 50 hertz, it could be uniform. But at high frequency, the top couple of turns in the transformer may take the hit more than the other turns, and you could have breakdown there. But we are not going to worry about this in power systems analysis. We worry only about what you see here. So we'll continue with this next time I see you, which will be Wednesday. Yeah. Okay, thank you very much.